Thank you very much. Yeah, it's a real pleasure to be here. I'm happy to be part of this great workshop. So what I'm going to talk about today is compressed sensing when you have Poisson noise. And one of the contexts in which Poisson noise arises is when you have very low levels of light and you're collecting data by measuring photons hitting a detector. And so it occurs in low light settings, or in other words, in dark settings. And so this is the dark side of compressed sensing. And it's joint work with my graduate student, Xin Jiang, and my colleague in Wisconsin statistics, Garvesh Raskuti. Okay, so this is a problem that arises in a number of different application settings. So those of you familiar with compressed sensing perhaps have seen this schematic before for a single pixel camera based on the principles of compressed sensing. And the basic idea is that you would take a scene and project it onto an array of digital micromirrors, and then roughly half of those micromirrors would project or reflect the light onto a photodiode, and you would collect a measurement. And you would collect a sequence of these measurements, each measurement corresponding to a different array or pattern of mirror orientations. And from those measurements, you'd like to reconstruct the scene. So if your scene is very bright, then this is a very viable idea, and Rice has built some beautiful prototypes demonstrating it. But as people have increased their interest in this area, companies like TI have tried to build faster and faster micromirror devices so that you can change the orientation of these mirrors very quickly or collect a large number of measurements in a small window of time. But as you try to push the limits of this idea, then Poisson noise rears its head. So the way to think about it is like this. Let's say that we give ourselves a time budget of t seconds over which we want to collect all of our different measurements. And we are going to collect n measurements. Then roughly the number of photons that we're going to be able to collect in each one of those measurements is on the order of t over n. So if we fix our time budget t and try to increase the number of measurements we collect, and then each one of those measurements is going to become noisier and noisier, and we're going to start having the errors in our measurements be dominated by these small numbers of photons, which are characterized by Poisson noise. And even aside from this setting, we see photon limitations arise in applications like spectral imaging, where not only do we want to understand, say, the spatial content of a scene, but we'd like to understand how our image of a scene changes as a function of wavelength of light. And so we're interested in reconstructing this kind of cube of data, space versus wavelength. And in general, as you increase the number of spectral bands, or the number of different slices in the stack, then the fewer photons you have per spectral band. Now in general, these data cubes are really big. There's a lot of voxels in them, or a lot of pixels in each slice, but there's also a lot of redundancy. And so it seems like a really natural fit for the ideas of compressed sensing. But very quickly, as you try to get high spectral and spatial resolution, you start having small numbers of photons in each bin, and you have some significant challenges. Now, in addition to having these problems arise in imaging contexts, we also see them arise in network contexts. And this is something that I worked on with Robert Calderbank a few years ago, our afternoon speaker. So in this problem, you could imagine having a router that's receiving a rapidly arriving stream of packets. And what it wants to do is to count how many packets are coming from different sources. And you would want to keep track of this for mostly billing data and also intrusion detection. And in these counts, most of the counts are very small or close to zero, but a few of them are really big. And you want to have an accurate measurement of how many packets are coming from these heavy hitters. Unfortunately, the standard kind of DRAM memory technology that they like to use is just too slow to keep up with modern data rates. And so routers are forced to use very fast but very expensive SRAM technology. And so again, we'd like to maybe consider building mechanisms for counting these packets coming from different sources that uses this fast technology but only uses a little bit of it. So only uses a small number of these memory chips. And you could imagine trying to do something like this using compressed sensing. But again, because we are counting discrete events, then we face the problem of Poisson noise. Okay, so in general, this is the problem setting that we're going to consider. We're going to observe a vector y of measurements, and conditioned on the intensity. They're all independent of one another, and they have intensity T, A, F star. So F star is the image or the signal that we want to reconstruct, and it has P pixels or parameters. We're going to assume that it is sparse in some orthonormal basis D, and that it has an L1 norm 1. So you can think about all of the signals in this function class as having the same overall intensity or overall brightness, if you want to think about this in an imaging context. And then that's going to be multiplied by a sensing matrix A, and you can think about A as corresponding to, for instance, the arrangement of these mirrors in the Rice single pixel camera. And then this is all going to be multiplied by a scalar T, which corresponds to the total amount of time that we're going to spend collecting our data. And you can think about T, therefore, as corresponding to a measure of our signal to noise ratio. And so all of our signals have the same overall brightness level, but by controlling how much time we spend collecting data, we control how many photons we're ultimately collecting. Okay, so within this context, our goal is to figure out what F star is. So we want to take the data Y and we want to enhance it, which isn't working. Okay, I had a good joke on here, but it was a video and we just couldn't get it to work. I apologize. But without the joke, our goal is to reconstruct F star from Y, and what we'd like to understand is how our performance or our error decay rates depend on N, the number of measurements we collect, P, the number of parameters or pixels we have, T, how much time we're going to spend collecting all this data, D, our sparsifying basis, and A, our sensing matrix. And what we'd like to understand is what fundamentally limits our sensing capabilities. So as some of you here might know, this is a problem that I've examined in past work, but that work only established upper bounds. And those upper bounds revealed behaviors that were not aligned with sort of the conventional wisdom of compressed sensing. And so it wasn't clear if that was an artifact of our analysis or whether those bounds were tight. In the work I'm showing today, we have both upper and lower bounds that are tight, so we have a much better understanding of what are fundamental limits and not artifacts of our analysis. You could also imagine asking a question like, if I have a fixed time t over which I'm collecting my data, is it better for me to very rapidly collect a large number of measurements where each one of those measurements is going to have a small number of photons and therefore be low quality? Or is it better for me to have a small number of high quality measurements? Right? And so we'd like to understand what the trade-offs are there. And finally, we'd like to just understand, well, what are some of the key ramifications of Poisson compressed sensing? Is this just more of the same, or are there some unique effects that are happening here? And what I'm going to do is just kind of give you some spoilers right off the bat, and you can see where we're headed with all of this. So the conventional wisdom with compressed sensing that was established, for instance, in Gaussian or maybe bounded noise settings, tells us that our error decay rates are, for the most part, independent of whatever our sparsifying basis is. So if we're collecting, say, Gaussian ensemble measurements, doesn't matter if we're sparse in a Fourier basis or a wavelet basis. And the conventional wisdom tells us that we don't do much worse with compressed sensing than we would have done if we had had some oracle information about where the non-zero coefficients were and measured them directly. Okay, so those are the kind of main talking points that you see in a lot of the compressed sensing literature. What we're going to see in the Poisson case are two key differences from this. First of all, we're going to see that the rates can depend very strongly on what the sparsifying basis is, and we're going to see why that happens. And in addition, we're going to see that depending on your sparsifying assumptions, so in some contexts, you can do far better than compressed sensing. So in here we said that, well, compressed sensing is sort of the optimal thing to do because even something with a lot more information doesn't do a whole lot better. In the Poisson case, that's not the case at all. There are things you can do that are a whole lot better than compressed sensing. And we're going to see why that is and how those situations arise. All right. So the first thing point I want to make is that this is not sort of the typical CS problem. And one of the reasons for that is that we have physical constraints that we have to take into account. And the way that I think about this that makes these constraints intuitive is I think about this sensing matrix A as describing, for instance, the propagation of light in a camera. So that an element of this matrix, Aij, would correspond to the probability of a photon coming from location J in my signal, going through my camera and landing at location I in my detector array. And once you think about it like that, once you think about it as these probabilities, then these constraints that I have listed here are pretty natural. Since they're probabilities, they all have to be between 0 and 1. They can't be negative. And we have to have probabilities sum up to 1. So we can't have more photons hitting our detector than are coming from our scene, right? So very simple, natural constraints. But unfortunately, if we think about typical compressed sensing matrices, Rademacher ensembles or Gaussian ensembles, they don't satisfy these constraints. And so we can't just do some minor modifications to the existing theory and expect to really make headway in a meaningful sense. Okay, so there are a few ways that you could sidestep this. And what Robert and I considered a few years ago were some methods for generating sensing matrices based on expander graphs. Today I'm going to focus on an alternative approach where we say let's start with a sensing matrix A tilde which satisfies, say, the restricted isometry property. So this is the sensing matrix we'd like to use, the sensing matrix we have all kinds of insight into based on the body of CS literature. And then what we're going to do is we're going to take that kind of ideal sensing matrix and we're going to add an offset and rescale it so that we satisfy all the constraints that I had on the previous slide. So now we've got a sensing matrix that's physically realizable, but it under the hood has a compressed sensing matrix that we'd ideally like to work with. And this, by the way, is exactly what is happening with something like the Rice single pixel camera. They start with a sensing matrix based on a Rademacher ensemble where everything is plus or minus 1. But what they actually implement via these mirrors is a matrix that has rescaled zeros and ones. So it's that Rademacher ensemble plus an offset and then renormalized. Okay, so what I said a few slides ago is that we observe Y coming from a Poisson distribution with intensity TA F tilde. And what we can do is we can use this sort of construction of A to understand what's going on here. So what we're really interested in measuring and what we understand the best from most of the CS literature is T A tilde F, where A tilde satisfies our restricted isometry property. And for just a little toy problem, I've plotted that T A tilde F star in blue here. So this is the ideal signal that we'd like to be able to measure if we didn't have any physical constraints. But because of this construction, that ideal signal is renormalized. So instead of having an amplitude that's on the order of 15, we have an amplitude that's on the order of 1. And then a constant offset has been added to it so that the observed intensity, before we even have any noise, corresponds to this red signal. Okay, so we'd like to measure the blue. We can't do that in a physically realizable way, so we end up measuring the red. And one of the challenges of all of this is that, as some of you may know, if you think about the variance of a Poisson random variable, it's equal to the mean. And so when we add this constant offset, we increase the mean of our signal, and therefore we increase the variance. And so this is the reason why trying to think about compressed sensing with Poisson noise is particularly challenging. Okay, so we studied our Minimax rates in several different settings. So we're considering signals coming from this class F, where everything has sort of the same, all the signals have the same brightness of 1, and they are all sparse in a orthonormal basis, D. And we then choose the best estimator in a class of estimators and look at the squared Euclidean norm of the difference. And what we can show is that in high intensity settings, where T, the amount of time that we are spending collecting all our data, is large, then this minimax rate is S log P over T. So there's a few things to note here. First of all, N, the number of measurements that we've collected, is not appearing. And instead, we're seeing T. So the data acquisition time t is really controlling how big our error is. And as I said at the beginning, you can think about this as a measure of our signal to noise ratio. And so it sort of makes sense that this plays a key role in these minimax rates. In addition, one of the questions that we posed early on was, is it better within our sort of fixed time window to have lots of noisy measurements or a small number of high quality measurements? And because n, the number of measurements, does not show up in this rate, it tells us that they're essentially equivalent, that there's not a strong advantage one way or another. We need n to be big enough so that our sensing matrix has these rip-like properties. But once we pass that threshold, it doesn't matter how big n is. And so you can choose when you're making a system to make n in a way that's just whatever is convenient or cheap or easy to build. Okay, so this is what happens for large values of t. And we actually simulated this kind of setup. And we see for large values of t, the mean squared error is decaying like 1 over t, just like the theory predicts. But this isn't happening for all t. So as I said before, this is only true for large values of t. And we see that there is this elbow in the rates. And when t is not big enough, we actually have pretty poor rates. And these rates are different for different sparsifying bases. And the location of the elbow is different for different sparsifying bases. So what we're going to do now is think about what happens at low levels of light or small values of t, and why all of these things seem to depend on our sparsifying basis. Excuse me. So essentially what's happening is that when t, the amount of time we have to sense our data, is small, then our measurements are very noisy, and so it's very difficult to get an accurate reconstruction. And so our mean squared error is actually going to basically correspond to everything in the signal that's not constant. At some point there's so much noise that all we can really estimate is the overall intensity of the signal and none of its fluctuations or variations. So we've got the signal f star minus its mean, and then we look at the difference, Euclidean norm squared. And in the subsequent slides, I'm just going to call this residual energy. Right? I'm taking my signal, I'm looking at its residuals from its mean, and I'm measuring the energy in that. And so what we'd like to do is to take this bound and say, well, what are the corresponding minimax rates when t is small? And what we're going to find is that this residual energy can be very different depending upon your sparsifying basis d, and that's why we get these very different rates and these very different elbows in the rates. Okay, so in fact, if we were to return to this little simulation example that I showed you before, we see that these kind of constant levels before the elbow correspond exactly to these residual energies that I was talking about. So this is borne out in simulations as well as in our theory. Okay, so how do we come up with minimax rates? So essentially what's happening is that we've got sort of two geometries that are in tension with one another. First of all, we've got the geometry of sparsity. We're only interested in sparse signals. But secondly, our signals have to be non-negative, right? If our signal corresponds to, say, the rate at which photons are coming out of a scene, that has to be a non-negative thing. And so the geometry of the non-negativity and the geometry of the sparse assumptions are interacting with each other. And that's why we see these different rates. And so what we're going to do is characterize this with something called a k-sparse localization constant that we introduced. And basically, it's the following. We're going to assume that our basis has one basis function which corresponds to a constant or a DC offset, which is common in, say, Fourier bases, wavelet bases, etc. And since we know the overall brightness of our scene is 1, we don't have to worry about it, so we're just going to focus on everything that's not the constant background level of the signal. And then we're going to say, okay, let's think about signals that we can construct that are going to be zero mean and that are k-sparse in this basis. So we're going to consider signals V, which are k-sparse, and where the non-zero coefficients are restricted to be plus or minus 1. So if you guys are familiar with different lower bounding techniques for minimax rates and the kind of hypercube arguments that are commonly used, that's where this is coming from. We're saying, well, the non-zero coefficients lie on the vertices of a hypercube. And so we're saying, okay, for these kinds of signals, which are sparse, but where the non-zero coefficients have roughly uniform amplitude, how big of an amplitude can my signal have? And that is going to tell us something about how what we need to do to ensure that our signal is non-negative, right? If this maximum amplitude is really high, then we have to add a big constant offset to have a non-negative signal. And so what we can do then is we can use this constant in order to assess our minimax rates. Okay, so maybe this seems a little abstract, and I'm going to break it down into some specific examples for some specific bases in just a second. But first, let me just sort of give an overview of the main theorem. So the minimax lower bound in these very low intensity regimes is dominated by signals with very low residual energies, where the signal is roughly as flat as it can be while still being a sparse signal. And so in that case, our minimax rate is lower bounded by maximum over all k between 1 and s of k over p squared times this k-sparse localization constant. And our upper bound in this small intensity regime is slightly different, and it is controlled by a parameter mu, which corresponds to the highest amplitude basis vector in our sparsifying basis, times our sparsity level s. So let's just think about what these things look like for some specific examples, and then look at some plots. So for signals that are sparse in a discrete cosine transform or Fourier basis, if we were to work out what these constants were on the previous slide, then the lower bound looks like 1 over p, and the upper bound looks like s over p. And if we were to look at a discrete wavelet transform basis, our lower bound is s over p squared, and our upper bound is 1. And in general, remember this sort of intuition that we started with, our rates are controlled by this notion of residual energy. And so when we compute these lower bounds, the lower bounds are dominated by the flattest S-sparse signals in our function class f. And so for some bases, it's easier to make a very flat signal with low residual energy than others. And similarly, for the upper bounds, they're dominated by how peaky we can make our functions, given that they have to be S-sparse in our sparsifying basis D. So with some bases, it's much easier to approximate a delta function while being S-sparse than others. And so it's easier to build peaky signals than others. So let's see this. So here, I'm considering the discrete cosine transform basis. And I have plotted two different signals. So the blue signal corresponds to the peakiest S-sparse signal that I could construct in this basis. And the red signal corresponds to the flattest S-sparse signal that I could build in this basis. So the red signal has very low residual energy and dominates our lower bounds. The blue signal dominates the upper bounds and has a very high residual energy. And what we see is that if we were to take this sort of general framework for constructing different signals that are sparse in the basis and look at how our mean squared error scales with p, that the rates are very much in line with the theory and the bounds that are presented on the previous slide. And we see something similar happening in a wavelet basis. We can construct things that look very peaky. This is almost a delta function, so it's a little bit hard to see. And signals that look very flat. And depending on whether the signal is flat or peaky, we get very different rates that, again, correspond exactly to our theory. Okay, so let's just see one of the kind of key ramifications of all of this. So like I said in the beginning, the conventional wisdom of compressed sensing is that we do nearly as well with compressed sensing as we would if we knew where all the non-zero coefficients were and just measured them directly. So what I'm going to do is compare compressed sensing with an alternative measurement scheme in this Poisson noise case. And we're going to see that that conventional wisdom does not hold up. So the alternative measurement scheme that I'm going to consider here is just simple downsampling. So if you want to think about a camera, this corresponds to a really low resolution camera. And so that's what people actually use in practice for low light imaging for the most part. And we're going to consider a special case of sparse signals where we are sparse in a wavelet basis. And of the S non-zero coefficients, S prime is going to denote how many of them are at coarse scales. Right, so you can imagine if you're doing some sort of low resolution downsampling sensing, then you're getting a pretty good idea of what these S prime coarse scale coefficients are, but you're not getting any information at all about the fine scale coefficients. Okay? So we analyzed this in theory, and we also conducted simulations, and they matched exactly. So what we're doing here is we're looking at the mean squared error versus how much time we're going to spend acquiring our data. And the red curve here corresponds to the compressed sensing result, which is the same curve that we were looking at in earlier slides. And the blue curves correspond to this very simple downsampling scheme, where we're just collecting a low resolution picture of our scene for different values of S prime. So when S prime is 8 or 10, it means, I'm sorry, in this example, S, the total number of non-zero coefficients is 10. So when the S prime is 8 or 10, it means most of our non-zero coefficients are at coarse scales. And so we see for smaller values of t, there's a huge advantage to just trying to essentially measure those non-zero coefficients directly via this very simple downsampling scheme. And that you don't really get better mean squared errors via compressed sensing until your light levels are very high. So this, as I said, goes against a lot of the conventional wisdom for compressed sensing, and I think has some important implications for how we should think about building hardware. So if I want to build a night vision camera, for instance, that's going to try to produce images with very small numbers of photons, then my inclination might be to say, well, let me use compressed sensing. But what this result tells us is that we're not really going to get a huge advantage out of compressed sensing until we are in very high light settings, in which case we might not need a night vision camera at all. So now, of course, this is for one specific sparsity model, but it showcases, I think, how the interaction between our sparsifying assumptions and our various physical constraints can lead to results that are very different from what we might kind of naturally assume based on some of the other literature. Okay, so this is just a recap of some of the main ramifications that I mentioned at the beginning, but maybe they'll make a little bit more sense now that we've gone through all of this. So the conventional wisdom says it doesn't matter what our sparsifying basis is, and we're not much more worse off than if we knew where all the non-zeros were ahead of time. Whereas with Poisson noise, we really have neither of those things happening. The rates, at least in the low intensity regime, depend very much on the sparsifying basis. And at least in certain sparsity situations, we can do far better using non-compressive measurements and just trying to get highly accurate measurements of some of the non-zero coefficients rather than getting terrible measurements of all of the non-zero measurements. Okay, so that's pretty much all I have on work that we've finished. I just want to say one thing very quickly about what we are working on now, and so I'm not going to give you any solutions, but I think it's pretty interesting. So all of the analysis, especially for the upper bounds that I presented here, is based on trying to estimate our signal by saying, let me search over all kind of coefficient vectors and find one which is, gives us a low Poisson negative log likelihood and which is sparse as measured by an L0 norm. And we do this analysis using ideas from coding theory, which means that it's really easy to use an L0 norm and it's really hard to use an L1 norm. Of course, I showed you a whole bunch of simulations, and they were all based on algorithms, which are also using a negative Poisson log likelihood, but, oops, typo, an L1 norm for my regularizer, because that's what we can tractably compute. And so there's sort of this mismatch, which you can't see here. This should be L1. There's a mismatch between what we can say theoretically and what we can actually compute in practice. And it's a little bit dissatisfying. We thought a lot about it, and it's very challenging to get around. So what I'm exploring right now is an alternative approach that's much more lasso-like. Where what we're going to do is we're going to, instead of using the Poisson log likelihood, just use a regular old squared error data fit term plus a weighted L1 norm. And what we're going to do is choose these weights very carefully in a way that's based on Poisson concentration inequalities, so that instead of taking all of the Poisson noise into account through the log likelihood, we're going to take it into account by setting up these weights. And what that's going to allow us to do is to have a single framework where we can do both analyses and practical algorithms. And while our current rates are tight, and I don't think we'll be able to do significantly better, this is going to allow us to analyze much broader classes of problems without having to worry about quite as many roadblocks as we had to work around in the work that I just presented. All right, so with that, I'd just like to invite you all to be seduced by the dark side of compressed sensing. And the work that I presented here today is posted on Archive and was supported by NSF, DARPA, and AFOSR. Thank you very much. Yes? Mm-hmm. I haven't looked at it, and in fact that's one of the reasons why we're doing this more lasso-like stuff currently, because it is very difficult to handle compressible and non-sparse signals using this framework, especially for the lower bounds. With the upper bounds we have some nice tools, but with the lower bounds what you're describing is pretty challenging to work with. And I think once we develop this lasso-like framework, we are going to be able to answer those things. That said, in practice, what you're describing is a problem. So you're saying, so what Petros is saying is that you could imagine having a signal which is not sparse in our dictionary D, but where we've got some coefficients which are really big and others which are very small but not exactly zero. And so we might be okay with not estimating them, but all of those are going to kind of contribute to our signal and increase our measurement variance. And so that can really make it much harder to accurately estimate the signal if you're not careful. But it's not well understood exactly what happens there, and that's one of the reasons why we're considering this new framework. Yes? Mm-hmm. That's also a good question. So with what I described here, you could imagine starting with like a Rademacher ensemble where basically essentially half of your sensing matrix elements are ones, right? And that's where we were able, let me just start that over. Right. It really depends on your sparsity model. So if you are sparse in, say, the canonical basis, so like if you're trying to collect an image of the night sky with some stars, then you can have a big advantage by having each of the rows of your sensing matrix be also sparse, because then you're not having this sort of folding of your signal as much, and it can really help a lot. On the other hand, if your signal is sparse in something like a wavelet basis, then you still get the folding even with that smaller number of zeros in each row of your sensing matrix, and you don't get the big gain. So I don't actually have rates that make that explicit at this point, but that is something that we've seen borne out in simulations. And so in these sort of low light settings, having something sparse in your actual signal basis is a huge advantage, and really mitigates a lot of the challenges that I've been mentioning here.